So we've been training reasoning models kind of all wrong. Not wrong in a 10% better or worse kind of way, but structurally wrong. Just the same way as we didn't get supervised fine-tuning right the first time, or RLHF. This video discusses the kind of mistakes that were made, and how we might think about fixing them going forwards. There's a pattern here. Each time the field started with a case-by-case assumption. Cover enough examples, cover enough situations, and generalization happens as a byproduct. And each time it turned out the real goal was something more meta than that. The second half of this video talks concretely about ways we might go about this, but the why matters too, so I'm going to build that argument first. So we'll start with instruction fine-tuning, then move on to the RLHF, and then we'll end up at the RL for reasoning, and we'll go into that in depth. The Flan paper in 2021 showed that learning on 1,800 general topics was enough to achieve some degree of generalization. And so the takeaway was cover enough topics, achieve generalization. Then Lima came along in 2023. Now this was like 1,200 carefully chosen instruction pairs. And while these pairs were carefully chosen, they weren't chosen for covering a bunch of topics, they were covering a bunch of forms. And the results were competitive with models trained on orders of magnitude more data. So that changed how people thought about what the instruction fine-tuning was actually doing. It wasn't teaching content, it was teaching the inclination to answer. So the goal of this instruction fine-tuning was not to train the model how to answer specific questions, but to give it the disposition that questions deserved answers, and this idea generalizes far better. So reinforcement learning from human feedback followed the same arc. The initial framing was show the model what responses are preferred for lots and lots of examples. But the constitutional AI from Anthropic showed that just by giving the model a constitution to follow, you could replace thousands of examples of hand-tuned contrastive pairs for the human feedback by the overarching idea of how to be harmless but helpful. So for example, with Claude, I find that it's a generally helpful model but will contradict me if necessary, whereas other models are notorious for being super agreeable, which is probably arising from the human feedback data whereby the models learn to be sycophantic rather than really that they ought to be helpful. So the internalization here is the meta goal. Rather than giving it lots and lots of examples of how to be helpful and not harmful, we give it the overall idea of what it's like to be those things, and that's a win. Now look at where RL for reasoning is today. So this is a graph from the Quen 3.5 technical report, and it shows how they have scaled the number of training environments and got better results. So the dominant story is build more in RL environments, cover more tasks, cover more domains. Dario Amadei put it explicitly in a recent interview. The number of environments is now the key scaling axis, analogous to how data volume was the key axis in pre-training. Cover enough tasks and generalization follows as a byproduct. But notice, that's the Flan assumption applied to reasoning, and we know how that story went. So my perspective is that these environments don't matter. The environments are really the curriculum rather than the objective. Just as in schools, we don't really teach algebra so that students can solve equations in later life, although I guess some will do that. Really, we're teaching algebra so that people think in a structured way, so they get to understand the feeling of doing that. Learning how to do algebra is kind of the vehicle for actually understanding how to do structured reasoning. And the structured reasoning is the actual target of this learning in school for most students. So there's some evidence that we haven't really covered that generalization gap yet. So the current reasoning models show a strong grasp of maths and code and these other verifiable reasoning domains, but as soon as you step outside that, they're much, much more brittle than you would expect. Now that brittleness is a symptom of a problem. If we were actually teaching the models how to think, the idea would transfer. But the fact that that reasoning skill doesn't transfer very well really shows that we're teaching models how to reason about particular problems rather than how to do the skill of reasoning. Now, one of the problems that people point to with reinforcement learning is that each rollout really only gives you one bit of information. Did you get it right or not? And on its face, this is true. The verifiable rewards just tell us whether we got the answer right or wrong. So in an academic setting, this would be like grading a student only on their final answers and we're never looking at their working, never telling them how they got an answer wrong and how they could improve. And in fact, lucky guessers would get rewarded, whereas careful reasoners who slip up on arithmetic would get penalized. So now let's think about this task a bit more broadly compared to this 1 bit per rollout framing. One of the key things between most of the pre-training and mid-training that is going on and these reinforcement learning methods is that we're actually doing this in a sequential way. The other things could all be done in parallel, which is super efficient on GPUs, but here we're paying the cost of rolling out every example individually, which is expensive. So since we're doing these serial rollouts in a grindy sort of way already, maybe there's a way in which we can exploit just adding a factor onto that, which will make each of these rollouts far more valuable to us. So the rest of this video is just going to discuss some of the ways in which we could get richer reward signals from this grindy process. So I'm only going to cover a few ideas here, and there are many more, but hopefully this kind of opens a discussion and there's clear ways forwards through this. Now, one underexploited idea could be from the work of Denis O, which talks about how base models can use consensus as a training signal. The key idea is that if you've got bad reasoning or you don't know what you're doing, you can get the answer wrong in many different ways, but you'll get many different answers. But if you do know the kernel of what's going to work, you'll get it right in the same kind of way. This means that if you have a model which can agree with itself a lot of times, that is probably the right answer, and then you can use that as a training signal. Now, this is not so useful when you actually know the end result, but you could imagine taking parts of an argument leading to a result where you don't know whether that part of an argument is correct or not, and then getting the model to react to substitutions of arguments in different thought streams. So here we're really exploiting the fact that the model has a lot of self-knowledge, which we're just trying to extract from it. Another path could be looking at whether we can get token-wise supervision. Now, an ordinary reinforcement learning with verifiable feedback thing will give us 1 bit for every rollout. But we also know that we can get more supervision signal if we had, for instance, a teacher of some kind. Then the teacher rollout, or even our own rollout, could give us supervision at each position. So this goes back to the hidden knowledge idea, where rather than just looking at the individual tokens which were chosen, you can look at the near misses, which are also very informative. So another thing you can do is have a teacher model from which you're distilling, where you look at how the student is rolling out. This is an on-policy rollouts, and the teacher looks at those rollouts, and then by some dint of it being better in some way, you can then give feedback which is relevant on a per token basis. So let's go through some of the ideas for what that teacher might be. So one choice might be just having a larger model. Hopefully the larger model would understand more about the problem, be slightly forward-thinking in its reasoning, and thus be able to teach the student. Even when presented with a student's rollout, it could have a verdict about each of the token positions. Now this may sound super expensive, but since the rollouts are presented to the teacher in parallel, the big teacher may have distillable knowledge quicker than the student can roll out these examples. Another idea would be to have the teacher which has privileged information. So maybe you have an actual proof that is required to get to the answer, which the teacher knows ahead of time, like a cheating teacher idea, and then the student comes along without that preparation. So you could even imagine the teacher being smarter, or the teacher could be the student itself, but without the cheat codes. Another possibility would be to take successful rollouts and use those as pre-reading material so that the model is smarter when it essentially marks what an unaware student does during its rollout. Another idea might be have a non-causal model, so a model which can look forwards in its reasoning as well as backwards, and so be better informed in that way. We'll talk a bit more about that coming up. So now I've talked a little bit about these on-policy distillation kind of methods, which, spurned by the Thinking Machines blog post, kind of sprouted up in January 2026, I guess or the ICML submissions. But now let's think of some architectural changes we might experiment with. So as I explained before, for pre-training and instruction fine-tuning, for instance, we're doing this all in parallel. This is super efficient on our hardware. All the tokens in these examples can be processed in parallel and learnt in parallel. But when we're doing RL rollouts, we're actually doing this serially. And since we're paying this serial cost, this kind of opens the door to much richer kind of signals that we can use as we're rolling out. And these signals are ones which wouldn't be available in the parallel setting, but we can always use them even at inference time fairly cheaply compared to the cost of the pre-training. Okay, so here's a pretty simple idea, somewhat covered by an OWLs video which I did earlier. Normally, each token we produce only sees the kind of result of the previous softmax and then goes forwards, token after token after token. But we do have the opportunity to kind of insert overlays at each token. We can actually make an assessment of what overlay should we be adding at this point. So you could imagine having something with an overall view of the state of play so far, which would then decide what overlay to apply going forwards. So here we might think of kind of atomic reasoning units. There's a DeepMind paper about this called, I think, Self-Direct. So in that paper, they had a whole bunch of different modes of thinking and they pre-planned how to use them. Here what we would say is we've got a whole different set of modes of thinking. We know what overlay would be applied in order to make that thinking to occur. We can actually then trigger it using some kind of classifier and then mark what these classifier transitions were doing at a kind of a higher level meta RL. So not only could we look at the individual tokens and give those rewards, but also give rewards for how we are doing the transitions and what these overlays would be. So here we're kind of supervising across the top and then changing some kind of overlay at each step or each phrase or each chunk. So the kind of strategies that you might learn are as on the slide. You may look at lots of rollouts to decide, okay, how did the machine think well? And then classify chunks of that reasoning. And then using that, you can form overlays. And then, okay, now we've got atomic things which you can use as a meta-reinforced learning chunking strategy. Now for another idea. As we move from token to token, the typical rollout process just takes the output of the softmax and puts it in as a discrete value at the bottom in order to get to the next token and so on. But we do know that somewhere in the middle of the transformer stack, it does have an impression of what process it's going through, not just what word it is on at the moment. And so maybe it would be nice to take that process and feed that in at a lower level so that that higher level idea can be part of the processing throughout. Now we can't do this when we're processing the tokens in parallel because we can't put the higher level stuff down at the bottom, this higher level kind of latent reasoning. But since we're rolling out in a serial way here, what we could use is signals from these higher layers and then just feed them in as part of, say, a LoRa adapter or something, which would essentially affect, starting at 0, how all of the subsequent tokens were produced. So instead of just taking the single value from the softmax, or even a latent reasoning kind of token, and then reusing that, we could take part of the higher level thoughts within the transformer from the step before and use that as an overlay initially started at 0, affecting all of the stages up through from the very first step. So here we could train these overlays in a more incremental way so that the model learns to take advantage of these higher level representations it itself is thinking through, rather than some thinking atoms we've derived from elsewhere. So this can also be cast in several other ways. One of the approaches which had a lot of interest on Twitter was this idea of measuring model entropy, or how the model thinks it is doing at the very top stage. But we could extend that to include these kind of layer-wise dynamics in a much more subtle way. Not only could the model look at measures such as entropy, but it also construct useful measures for itself so that it can direct its own forward-thinking process. Okay, so now for a third structural idea. So here's a very simple teacher-student kind of fix that you could do, is you could take a reasoning path which is a good rollout, even though it may contain problems, but then essentially duplicate it. So now the second copy of the rollout will be able to look back and see the mistakes that were made or the points which were reached and have a slightly different opinion about the quality of those steps. And this information gap might enable a teacher to backfill a student with forward-looking information. Now, an idea similar to this was actually noted in a Google paper at the end of last year, where they noticed that if you prompt a model twice, like even one of the big models twice, it can actually help it answer questions because the second version of the prompt actually knows how the prompt ends, and so it can interpret the beginning of the prompt more thoroughly than just having one copy of the prompt. Now, another thing to point out is that a well-trained reasoning model will probably try to restate the problem in its own terms as one of the very first steps, and so it would gain the benefit of seeing the prompt twice automatically. But that is why it's worth Google publishing this as a result for non-reasoning LLMs, so people can realize that prompting it twice with the same thing would actually give a benefit, because the fact that the models are actually doing this for themselves is hidden in the thinking tokens by the Frontier Labs. So these aren't just arbitrary architectural proposals. Each one of these maps to a different kind of meta skill that we'd like our reasoning models to have. Now, in the interest of time, I'm not going to go through these one by one. There's a blog post in the description below which actually fleshes these out a little more, but there's a common thread that's worth mentioning. Everything here is about giving the model access to information about its own reasoning process, and for it to glimpse its ability to steer that process. And that steering ability is not something it can learn from seeing lots of data on the internet. That process is purely seeing what other people do and learning to mimic it. Now, with these agentic RL models, what we want them to understand is that they have control of their own token destiny, as it were. Now, this is a thing that the standard training doesn't really do, but in my opinion, this is something which really matters. So overall, the big question is, are we teaching the models how to think, or are we teaching them how to solve problems? The key difference is that suppose I'm presented with a new website, I instinctively know how to find out how it works and to use it, rather than having to be shown lots and lots of different websites to hone my skills at all the different kinds of combinations. Simply by having a curious nature is enough for me to go and do that on my own. Trying to create this kind of curious nature is a kind of a meta-learning idea where I don't think the current emphasis on having many, many different RL environments is really taking us in the right direction. So if you've enjoyed this video, which has been researchy but also somewhat philosophical, please give me a like and a subscribe. I'll be tackling more paper-orientated research in upcoming videos. I'm just trying to experiment with different themes to find out what resonates with people. See you in the next one. Cheers.